My name is Chi Chow. I'm a long-time Yahoo. I've been here for over 10 years. I'm looking at the room here. I don't think I recognize a single one of you, so I'm sure you all are, joined Yahoo way after I did. But I want to introduce Ben, who's your speaker today. Ben and I go long times back. About 12 years ago, I went to Microsoft Research and I brought back Marmot, which was the first, one of the first Java to see research compilers. And I was doing my graduate PhD thesis, and Ben was an undergraduate at Cornell, and he was looking for work. And so I hired him. Did I hire you as an intern for the summer? And I think from there on, we basically built a great relationship. He actually came back to Yahoo in 2002 as a summer intern, and he worked on various projects, I think one of which is some sort of a conversion attribution type of work, which is related to data mining, data processing. And then he went on to finish his PhD at Stanford under Monica Lam, after which I think he joined MSR, right? Mm-hmm. And he's now at the programming languages group there, and has been doing great work, publishing at great places like SOSP. And he established himself as an expert in client-side security. So without further ado, I'm going to yield to Ben.
Okay, thank you very much for the introduction. This was great. I think I was an intern at Yahoo back in 2002, and the interesting thing is that summer I believe I was the only technical intern within the company. So I think they had a few marketing interns as well, but I believe I was the only one on the technical side, which was kind of interesting. In any event, so I work at Microsoft Research. This presentation is about some of the projects, actually two of the projects we did recently. The focus is on Ajax, performance and security of Ajax, and Web 2.0 applications. So let me start by showing you this. How many of you have seen this picture before? Anybody? Okay, one person. Okay, there you go. Two. So this comes from Flickr. This is state of Web 2.0 circa maybe 2003 or 4. Some of these companies are still around, so you can see things like Facebook. I guess Friendster is no longer there, so on and so forth. But sort of moving to slightly more technical side of things, this is what we experienced in the last 5 or 6 years. We basically had a transition from Web 1.0 to Web 2.0. So what does it really mean? So Web 1.0 is basically what we have over here on this slide. So we have server-side computation producing static HTML that is sent to the user's browser for rendering. Right? So the point here is that execution happens in a single tier, in this case on the server. Web 2.0 changes this picture quite drastically, which is to say that now we have a distributed application. So we have the server side, which is running something typically within a data center these days. But in addition to that, we also have execution happening on the client. The most typical situation for the client is JavaScript running within the browser. But you can have other options as well, like mobile devices and so on and so forth. Now, what is the advantage of this model? The advantage of this model, of the Ajax model, as they call it, is great responsiveness. So why do people like things like, say, Gmail or Facebook or sort of quick and responsive Yahoo applications? It's because for these applications, you don't have to go and cross the network divide for every single thing. Right? So quite a bit of execution can happen within the browser without requiring a network transfer. And that's really advantageous because, that makes these applications snappy, users react to that, and everybody's happy. Now, from the standpoint of developers, the fact that these are distributed applications leads to a whole bunch of unpleasant complications. Suddenly something that used to be under your control is actually outside of your control completely just because you have your code running on somebody else's desktop. And I'm actually going to talk about two relatively independent projects that we worked on recently. My background, as Chi Chow mentioned just recently, is in programming languages. And as programming language researchers, we generally tend to look at 3 specific applications. So these applications are performance, security, and reliability. And the 2 projects I'll talk about fall into the under the rubric of performance. The first one called Doloto, and the second one is a project focusing on security. I don't have anything focusing on reliability, today at least, just because I only have about 45 minutes, and I don't really want to run out of time. Okay, so the first project, Doloto, focusing on improving the performance of Ajax applications. Before I go into the sort of technical details, let me start by showing this application over here, Live Maps. This example goes back a few months, as you might imagine. They renamed this application recently. One more time. Now, if you look at this application, this looks just like any other web page. If you look under the hood, something else, something different, something quite different emerges actually, which is this application, its client side alone, contains over 70,000 lines of JavaScript code. Almost 3,000 functions, and in terms of the size, it's over 1 megabyte of code. So this is a complex application. Right? In addition to being sort of a large-scale, sophisticated application on the client side, it's also highly distributed in that it talks to a whole variety of backend services, some owned by Microsoft, others owned by other providers, to get information like traffic, directions, blah, 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 blah. So the point here is that a seemingly simple web page, so to speak, effectively turns out to be a really complex application. And you don't have to look at the backend to discover that. Clearly, there's a great deal more happening on the backend. But the front end of this application alone is already complicated enough to justify interest in optimization, security, and basically interesting research, which is what I'm going to talk about. Okay, so let me give you a little bit more motivation for Doloto. So it turns out that applications such as these, so like say Google Spreadsheets, Hotmail, Gmail, Google Maps, and so forth, if you were to go to them and basically clear your browser cache and look at what gets shipped over to you with Firebug, you'd discover that the majority of the stuff that gets shipped over to you is actually JavaScript code. So for something like live.com, it could be over 80% of the application download, which is JavaScript code. So code is actually the most significant component in most cases of what gets shipped to the end user. And that's very important and interesting. Why is that? Well, the problem is that a lot of code slows the application down. Right? Yet a lot of code is required because these applications, as time goes by, become more and more sophisticated and complex. They get libraries, plugins, extensions, and they start to approach in their complexity desktop applications. So basically we have this tension between moving code, moving JavaScript to the client to get better responsiveness, and the fact that execution cannot really start before the code is migrated to the client. So there's this unpleasant catch-22 and this circular dependency that we'd like to break. And that is really the focus of Doloto. So that was the motivation. How do we do this? Well, the ideas are really fairly simple. Let's focus on these 3 points over here on the screen. So we start by sending the smallest piece of code possible over to the client, over to the browser, so that the application can start executing right away. Right? Now, while it's executing, whenever extra code is required, the application is going to go over to the server and get that code. Secondly, whenever there is extra bandwidth between the browser and the server available, the server is going to actively push the code over to the client, to the browser, so that if the user is sitting there doing absolutely nothing, then eventually the entire body of code will be available within the browser. What are the benefits of these simple ideas? Well, the benefits are quite pronounced. So basically what we do is that we interleave code download and application execution. This is most noticeable in terms of faster startup times, right? So the application can start out almost right away because, well, the majority of code is not really needed for the startup, right? So we can start with the bare minimum, let the application run, and then whenever new features are required, the browser, right, the way we kind of rewrite this application, as I'll describe in a second, will go and obtain the necessary code from the server on demand. The other thing that's interesting is that rarely executed code is rarely downloaded, which is really nice if you think about building applications with libraries, which is to say if you use a library like, say, Prototype or jQuery, well, your application might only use, say, 20% of that library. There is really no reason to download the rest of it because they're just wasting capacity. So these are the ideas, and let me tell you about how we do this. So 3 steps. The first step is training. We try to understand how the application uses its code. The second step is clustering. We take the application code and essentially group related functions into chunks, right, into clusters together. And the third step is code rewriting. We take existing application code in JavaScript and we stub out code that doesn't need to be there, thereby reducing the amount of code that needs to be transferred over to the browser. Okay, so for those of you who have worked with compilers, this is basically profile-driven optimization. We essentially use runtime profiling to understand how the application uses its resources, and then based on that information, we proceed to rewrite the application to optimize things. So the first thing is to do training, right? How does one do that? So here's the setup, which is basically, so on the left-hand side we have a site such as, say, Facebook, for instance, right? So it's serving a bunch of JavaScript. Maybe it has, I don't know, 300 kilobytes worth of JavaScript code that's being sent over to the browser. We create this instrumentation proxy and we instantiate it on the same machine where you're running your browser. So any of you can go and use your laptop to profile Facebook code. The magic of the web is that, well, basically JavaScript code is in the open, which means that we can easily intercept it, right, sitting on localhost effectively, parse the JavaScript code, rewrite it to insert our instrumentation, and then send that instrumented code over to the browser, right? So how do we instrument it? We basically go and instrument every single function to record entry and exit times for that function. And then basically we try to group functions together into clusters based on first use time, right? And the idea is that we are trying to effectively identify high-level application features, and I'll show an example of that to you in just a second. So clustering. So what is that about? Let me show you this actually, which is the result of running Doluta on maps.live.com, which is that site that I showed to you a few slides back. So you probably can't see everything that I have, on this in this screenshot here, but let me point out a couple of things. So first of all, is there a laser pointer? Maybe not. Okay. So on top of the screen over there, it tells you that it found 6 clusters, right? So for this particular application run, it identified 6 different clusters. So these clusters generally correspond to high-level application features. So the initial loading of the maps page will be 1. Maybe double-clicking on the map will be cluster number 2. Maybe asking for directions will be cluster number 3. Maybe printing the map or directions will be cluster number 4. Maybe help functionality will be cluster number 5, and so forth. Right? The idea is to package these up into groups so that they can be requested from the server together. Okay, so there are other sort of interesting things to point out here. For instance, there are different ways for this machine learning kind of machinery that's underlying this to work. So we can produce, based on the same run, we can produce multiple clustering strategies. So this is the default one, but we can also choose, for instance, fine-grained over there at the bottom, which would produce a whole bunch of really smallish clusters, which is probably a crazy idea for regular kind of fast connection, but not a bad idea if you're thinking about a mobile setup. So the idea here is that basically this is like a retargeting compiler, which is to say that based on the same information, it can produce different it can repackage your code differently, which is really quite powerful. The developer really doesn't have to get involved. These different versions can be produced based on the same code base automatically, and that's really quite nice. And the final bit is rewriting. So once we've done all of this training and clustering, all of that magic, we can now take the code, the original JavaScript code, which is readily available, right? You can go to Gmail, save their JavaScript on your disk, and that's pretty much what Doluta does, right? And then take that, parse it, and then rewrite it. How do we do this rewriting? So the idea is that we basically stub out code that's not immediately necessary. Let me show you an example of that. So consider this function over here on the left. Suppose this is a large, kind of long function, maybe hundreds of lines of code. Who knows? If it's a small function, then there is really no reason to bother with it in the first place. What we do is we replace it as part of this code rewriting with a stub that looks kind of like this. So a few things to point out about the stub. First of all, the signature of the stub is exactly the same as the signature of the original function. So the first time the original function was supposed to be called, the stub would be called instead. The next thing is that it is going to proceed to load the code, right, the actual body of the function from the server on the slow path over here, F1. So it goes and requests this information from the server. Here's something interesting, which is not only is it going to get F1, it's also going to get all the functions within the same cluster where F1 lives. Why do we do it that way? Why do we do clustering in the first place? It's in order to minimize the number of round trips we have to make to the server, right? Because otherwise, every single function you hit, you'll have to go to the server back and forth all the time, which will really kill your performance. This way, we identify that a particular feature, like say printing a map, is being used, and so the first function that's not there is going to basically introduce this kind of page fault, if you will, and then the entire functionality will be brought into the application, migrated over to the client if it's not yet available there. It could already have arrived there by now, we don't know. But if it's not, then it will be pushed over. Then we go and proceed to eval this code, right? So that's the wonderful eval feature in JavaScript. And the next thing is we apply this closure that we get by evaling to the arguments that we passed in. So far, so good. And then we also do other tricks, like we go and substitute this symbol. So F1 now becomes this real F1 closure, because that way, the second time we execute it, there's no need to call this stub because the function itself is already available. So that's great. We also do caching and so on. So that's the basic idea. Can anybody, I don't know, any JavaScript wizards in the audience? Well, I know at least one. Can you point out the problem with this approach? Yes, please.
The eval function is security.
Yeah.
Blocking on load.
Yeah.
That's one. Okay, any other issues?
What does load do exactly? How does
Load basically issues a synchronous XHR. Think about it as a synchronous XHR.
So it can request off a different server? Or is it going to load a script tag?
It's basically these no, it's not a script tag. It's basically a bunch of cluster files that are saved on the file system of the server.
So you can't load from a CDN or something?
You could. It's a matter of configuration. You could. Any other issues?
If there are multiple functions in the code,
Come again?
if there are multiple functions in a given code,
Right.
how do you want to find to a given function?
How do you what?
Find to the F1. How do you reach F1? If you load 5 functions
Right.
in this code, so how does this F1 find to?
Oh, there's some extra parsing machinery. Don't worry about it. That's not the problem. Anybody else?
Synchronous when you load.
Yeah, not that. Okay, I'll tell you the answer. All right, I don't think we're getting there. So the problem is this. Think about taking F1 and then calling F1.toString. The old version would produce that humongous function on the left. The new version, assuming we've never called this function F1 prior to calling toString, would produce this, stub on the right. So we kind of, made things not quite the same compared to what they used to be. Luckily, in practice, this doesn't really happen, but this shows you how tricky these, kinds of rewriting and optimization tasks can be in practice. Anyway, turns out that this is not the end of the story. Turns out that you can actually make this smaller still. So it turns out that this stub over here is very sort of cookie cutter code. The only thing that changes is basically F1 over there and then the parameter name. Right? There is no reason to basically transfer this cookie cutter code over to the client again and again and again. What we can do is basically we can use this eval, compression by eval technique to produce this stub through another level of calls to eval, which is really cool because basically we went from a function that was several hundred lines of code to one that was about, say, 160 bytes, which is what the stub is, to one that is about 20 bytes, which is what we have over there at the bottom. And it turns out that, all this compression actually pays off quite well. Well, how well? Actually, before I show you that, let me kind of tell you a little bit about how this is packaged together. So just so that we're on the same page in terms of rewriting and stubbing things out. So imagine a file, kind of the before picture, a file with 3 functions over here on the left. It gets replaced by these little stubs represented by those lines, and then the rest of the code. And then the rest of the code basically gets reshuffled, right, based on the clustering information we saw before, and gets saved into files on the server, things like c1.js, c2.js, and so forth. So the server doesn't really need to have extra support for this stuff. It's basically driven by the client. So that's kind of the deployment story. And basically the interesting thing is that you can actually profile and cluster your application without any access to the server. That's how we do it for just about any third-party site, because basically JavaScript is out there in the open. It's only when you have rewritten the code and you want to upload it somewhere that you have to worry about these things, which is really nice. You can basically test out this approach, see if you like it, and if you do, then you kind of bother to actually touch the server. You can really get a lot of insight into what's going on without affecting the way sort of the production application is run. So, experiment. So we went and experimented with a whole bunch of different popular sites out there, things like, I don't know, Google Maps, Hotmail, New York Times, Amazon, blah, blah, blah. We see pretty significant savings in terms of how much code can be stubbed out. So the amount of JavaScript code that can be stubbed out ranges from about 20% on the low end to about 80% on the high end. So a complex application like, say, Google Maps that has a great deal of functionality in it, well, for the initial run, for the sort of initial showing of the map, right, whatever Google Maps does on the first run, that functionality is really not required. It's fine to basically go and only bring in about 20% of the code and then load the rest of it whenever it's required or whenever there is nothing else going on. So you can see where these, just because the coverage of the application is actually fairly low for most of the ones we look at, maybe hovering around 40% or so, that's why you get really these great savings in terms of the amount of code you can throw away initially and then pull in on demand if necessary. In terms of, and actually if you look at the raw numbers, these were percentages, but the raw numbers are also fairly significant. So something the size of like Google Docs, you're saving, you don't have to transfer over hundreds of kilobytes, about 400 or 500 kilobytes in the case of Google Docs of JavaScript code. And so that's actually fairly important. That means that applications can start quite a bit faster. How much faster? Well, it turns out that we look at different network configurations using Network Simulator, and we discover that we make applications more responsive by about 10 to 40%. Which is really fairly significant, right? It's not really obvious how to achieve similar gains by, say, optimizing JavaScript alone, or, well, clearly getting similar gains just, by either just looking at the front end or the back end is actually fairly difficult. And this technique doesn't really require a lot of developer involvement at all, which is really nice. It's basically a deployment time tool. So we actually made a binary drop of Doloto available on the Microsoft Research site, and we got quite a bit of publicity based on that. We're also thinking about one of these days open sourcing the tool, because people have asked for various kind of customizations and ways to build this into their embed this into their build process and things of that sort. So we feel that maybe making the tool available in the form of the source would help with that. Okay, great. So that was the first topic that I wanted to cover. The second project, called Ripley, sorry about that. The focus of Ripley is on security, web application security. Okay, so remember this picture, right? Web 1.0 becomes Web 2.0. So in particular, application execution is distributed. In particular, it means that what used to be under the developer's control in the server, in the data center, is no longer sort of there, because execution happens in the client. And that means that, well, the portion of the application that runs in the client in JavaScript can no longer be trusted. And that has really unpleasant implications for how one can build applications, and that's really what Ripley is about. Now, before I talk about that, let me kind of give you a little bit of background, which is there are different ways to build Ajax applications. So some people, use a combination, say J2E and JavaScript, or PHP and Flash, or Silverlight and ASP.NET, right? So that's kind of one alternative, where you basically develop your client-side code and server-side code maybe at the same time, but kind of independently, and then you kind of put them together. And the disadvantage is that they can get out of sync, and things fall through the cracks, and so on. So people have proposed a different approach, which basically is called distributing compilers. The idea here is that you write your application entirely in a single language, like Java or C#, and then it's the job of the compiler to basically split it into the client tier and the server tier, right? And so one such compiler is a tool that we have at Microsoft called runtime. So let me jump into it and show you how that works. So you start with an application that you have in bytecode. In this case, we use .NET bytecode. And then Volta comes in, represented here with the meat grinder, and basically breaks it down into the client-side piece and the server-side piece. Both of them are still in bytecode. Okay, so far so good. And then it takes the client-side piece and translates it into JavaScript. And this last part is actually fairly complex, and that's why we have compiler engineers and people like that working on it, but it actually works, right? And so basically what it means is that we go, now this is discarded, but we go and take the client-side piece and the server-side piece. The server is in .NET, the client is in JavaScript, and then pull them apart like this, and this is the deployment story. So basically what used to be function calls in the original application now become RPCs. So you used to call function foo, now there is an RPC that goes and marshals the arguments through and then sends them over to the server, and then the result comes back, gets demarshalled, and comes back to the client. And this is the programming model that's been advocated time and time again in the past, and like I said, Volta is just one of several tools that exist in this space. Now, the problem with this approach is that the client really is not to be trusted, right? We talked about this before. So the developer, in fact, if you go out there and look at the book like the one over there, is basically encouraged not to trust anything that happens on the client side. So the view that they're encouraged to have is basically, that the user is basically this devil in the browser, which means that there is no data integrity, no code integrity, right? So just about any piece of data that comes from the client can be tampered with. Similarly, the code, the body of code that exists in the client can be also easily tampered with by just going into Firebug, right? It's really trivial to go and look at the code and change it, thereby changing the logic that runs in the client within the browser. Well, this is really bad news. Let me actually take this example, which is a bit extreme, but I think it illustrates this point really well, which is, think about this kind of prototypical, pet store application on the web, right? This shopping cart. I'm not selling pets here, I'm selling computer equipment. So there are mice, keyboards, blah, blah, blah. And imagine this written in a very Ajaxy way. So how would it work? Basically, you go and interact with the shopping cart, change, the number of items, add new items, add coupons, and so on and so forth. And then once you're happy with it, you go and send off the entire thing to the server for sort of completing your purchase. Right? It's great because the application is basically responsive more or less throughout the process. There is only a single RPC going off to the server, and before you do that, you can actually interact with the application in a way that seems very responsive, just because there is no communication with the network at all. Right? The problem is that this is not at all the way. This is completely insane, actually. This is not at all the way these applications are developed. If you were to look at, say, I don't know, Amazon.com and the way it does its shopping cart, you'll see that basically there's this constant chatter, this constant back and forth between the client and the server. Why is that? Just because seemingly every operation that happens within the browser requires a trip over to the server. Why? Because we cannot trust anything that happens in the client. The client can go and look at the JavaScript functionality here for adding up the items in the shopping cart and override that function to always return 0. So instead of paying $200 for whatever you're purchasing, you'd be paying $0, which is great for the attacker, and that's why developers don't really do it in this Ajax model. So Hopefully this is obvious by now, but there's this, there's a great deal of tension between responsiveness and security in this environment, right? So for reasons of responsiveness, you would like to use Web 2.0, Ajax, Silverlight, blah, blah, blah. For reasons of security, you basically want to position, to put everything, all the code you have, on the server, and that's it, right? So in that camp, you have things like CGI and PHP and ASP.NET. So the question that we are trying to answer with the Ripley project is, can we get both? Can we really get the best of both worlds? Can we hit that sweet spot? And we think we can. So let me give you the sort of guarantee, if you will, that we provide with Ripley. So with Ripley, placing the computation in the client does not reduce the computational integrity of the application. So what's the right way to think about it? So you take an application, a standalone application on the server, you split it apart. You just lost its computational integrity just because the client can do whatever. Now we protect it with Ripley. That protected application will produce the same exact result as the original application, as the original standalone application. Right? So that means that we recover the loss of security that we get by partitioning the application in the first place, which is really what makes this technology attractive. Questions? Okay, let me move on. So how do we, I'm actually doing well on time. How do we do this? Okay, so back to these triangles. Turns out that you can explain just about anything in this space by using 2 or 3 triangles. All right. So we have the server-side portion of it running in .NET, because that's kind of how Volta works. And we have the client-side portion, which is in JavaScript, because that's what we translate to, and that's what we can run within the browser. And the user is talking to the JavaScript part of it. The first step for Ripley is to create a replica of the client code and place it on the server. Right? So in a way, we undo the transition. Right? In a way, we undo this move that happened before when we partitioned the application. Step number 2 is to capture events such as keystrokes and mouse click that happen on the client over there that the user produces, and package them up and ship them over to the replica. That way, the client-side portion and the replica will have the same exact input, sort of the client-side sort of directly, and the other one indirectly because we make it so. And the last part is to create this Ripley checker, which is this little layer that sits in between. So the job of the Ripley checker is to basically go and observe RPCs. There are 2 sets of RPCs that exist here. There are untrusted ones that come from the client, this M' arrow over there, which is why there's this little devil over there, because those are not to be trusted, because who knows. And then there are the trusted ones computed by the replica based on this input, right? Because the replica is fully under our control. There is no, data manipulation. There's no code manipulation. Everything is great. So if you look at the left-hand side of this picture, basically we recovered the application the way it was, which is to say this is more or less the standalone application the way we started with. There is the server side, there is the client side. What used to be function calls is now RPCs, but that's a relatively minor difference when it comes to functionality. And basically, whatever computation happens, we only really trust whatever happens on the left-hand side, right? We still use, keyboard presses and mouse clicks, because that's how the application is driven, but we don't really have to trust anything that comes from the client, which is really nice. Now, the client-side portion of it is still there. Why is it there if we don't trust anything that comes from it? Well, it's there for responsiveness, right? We don't want to take an application that was really snappy and kind of like basically break it by removing the client-side portion of it. We still want that, yet we are not going to trust anything that happens there. We're going to essentially replay or recompute whatever is necessary on the server. Now, if you think about it, we don't even have to necessarily look at M'. If it's not our job, if it's not our goal to go and find bad guys, we can basically disregard whatever RPCs are, received from the client, because really, all that we care about already happens on the left-hand side. It's actually pretty great. So there are other possibilities in this model that exist and actually quite wonderful. So for instance, imagine the following. So it's this little trick that we call zero latency RPCs. So how does that work? So you have JavaScript running on the right-hand side in the client, and we have .NET, which is what the replica is implemented in, on the left-hand side. Now, .NET runs a fair bit faster than JavaScript these days, which means that if we were to take a JavaScript handler and start it at the same time, then the left-hand side, the replica would complete faster than the client. Right? So suppose it completes and it blocks on a database call. It needs some data from a database that it has on the server. It would proceed to go to the server, bring this piece of data, and have it available. Now, the client-side portion, the JavaScript, is still running. But since the replica already has it available, it might as well push that information over to the client. So by the time the client actually gets to that request, to that blocking RPC to the server, that information will already be present within the browser. Now, this is really nice if you think about it, because we're basically combining both performance and security. We're basically forced to pay for this extra security by placing extra computation on the server in this replica that wasn't there before. But we can sort of get some payback, if you will, by sort of volunteering this information and actually accelerating the execution of the application by using these extra cycles within the data center. Okay, so let's actually look under the hood just a little bit. And actually, before I do that, let me go back to this picture over here, which is the Volta picture. So you might be wondering, well, how do we do this replication? This seems a bit like magic. And it is, right? If you had an arbitrary JavaScript application, replicating the client-side portion, just an arbitrary chunk of JavaScript, running it on the server is really no easy task. There's no obvious way to do it. You could try to use, I don't know, Rhino. You could use a browser. You could instantiate a whole bunch of, Firefox instances. That's one approach. But, well, turns out to be quite inefficient. So our alternative is actually to observe that basically this client-side component in bytecode over here, before being translated to JavaScript, is functionally equivalent. So you might as well use that as the replica. Right? That's how we get a piece of .NET code and a piece of JavaScript code that are functionally the same. And that's really powerful. That's how we can get sort of this, that's how we can get to this picture over here, to this replication picture over here. And that's how we get these two things being functionally the same. So some other details. So how do we do this event capture on the client? Well, it turns out that because we control the framework, Volta in this case, it turns out to be not that difficult. It turns out that you can actually do it relatively easily by instrumenting things at the level of bytecode. Because we control the APIs, we can do this relatively well. We go and instrument this stuff to basically enqueue these events on the client side, buffer them up, and generally we try to piggyback on existing RPCs so as not to create extra network requests, because that really costs a fair bit performance-wise. So that's generally what happens in the client. Now on the server, there's quite a bit more to worry about. So remember, the problem is that we're creating these replicas. So if you're running, say, 100 of users per machine in the data center, which is quite a bit of users, quite a number of users. But we would have to run another 100 replicas corresponding to those users, which would potentially overload the server, and we don't want that to happen. So how do we manage to scale up in this situation? Well, so the naive approach is to basically take a whole bunch of browsers and run them side by side, right? But if you were to look at the footprint of a browser like Firefox or IE, you'd discover quite quickly that it's about 50 to 60 megabytes. That's the memory footprint. That means that there's no way you can run 100 of these side by side, even if you had a pretty sort of robust machine to your disposal. So what to do? Turns out that, well, we don't really have to have a full-blown browser. And the insight here is that on the server side, there is nobody there to see anything, right? We can afford to have a headless browser for all we care. Moreover, we can actually afford to have something that's much less than a headless browser. We can basically, what we did basically was build a replay emulator that only replicates, that only really properly emulates the dumb functionality that we need for our application. It doesn't have the ability to run, say, plugins, so it doesn't have the UI, doesn't really have all those other bells and whistles that a traditional browser would. And as such, its memory footprint is considerably less. So in our experiments, we see a memory footprint of about 1 to 2 megabytes per running replica, which is really quite nice. We've built a variety of different applications to basically demonstrate these ideas in practice, and we also experimented with a large application, Hotmail. It's really quite substantial to see what the overhead of replicating such a thing would be. Let me share some of these results with you as well. Actually, let me show you this last application over here, distributed online game. I think is actually great for explaining sort of the principles of Ripley one more time, which is to say that, well, so this is a distributed online game, right? This is a kind of scenario where hacking is actually quite prevalent. So in this case, there are two users, the kind of the blue ball and the red ball, and they're sort of chasing each other in this maze. And the way this application was written was that the move validity check, right? So you click one of your, you want to go to the right. There's functionality that sits there to see if it's a valid move. That check was located on the client, which meant that, say, the blue user who was malicious could go into Firebug and take that function and basically make it return true. What effect would that have? They would basically able to go through the walls, right? So this is one sort of canonical example of cheating in these scenarios. So imagine the following scenario. So suppose they move to the right 3 times, right? And in their modified version, they're able to go to the wall over there on the right and end up on the other side of it. Now these keystrokes, these right arrows over there, are going to be captured by Ripley and shipped over to the replica, which is running unmodified code. The replica will still run the original check, and it will detect that it cannot move to the right. It will basically end up staying in the same place where it started. Now, when the client side and the replica eventually report their position information, their state information over to the server, the Ripley checker will detect that, well, the client is saying that it's to the right of that wall in the middle, whereas the replica is saying that it's actually in the same place where it started. That discrepancy will be flagged by Ripley, and the client will be terminated. The cheating client will be terminated. Okay, so this is good. And now what happened? What happened is that Ripley was able to detect this sort of an exploit quite easily without knowing anything about the application functionality or about how the application is partitioned into the client side and the server side. Which means that the developer is more or less free to make these decisions about partitioning based primarily on performance considerations and such, and not really worrying about the application sort of security and integrity too much, which is really nice, right? Moreover, the developer doesn't really have to kind of modify their code either, because this replication is performed by Ripley itself. Okay, so let me go through this overhead. There are several dimensions of overhead. Let me see. So network overhead, CPU overhead, memory overhead. I talk about the memory overhead. It turns out to be relatively small, about 1 to 2 megabytes in our experiments. Memory overhead, we compress this event stream fairly well. The CPU overhead, we have some scalability experiments in the paper that I'll mention to you at the end. Let me skip this and actually go to the final vision for this project. So the vision for Ripley. So basically the philosophy for this project is security by construction. The idea is to be able to take a Web 2.0 application, Ajax application of some sort, and basically drop it into this Ripley server farm, thereby protecting it without involving the developer in this process. Okay, so some paper references for you from recent conferences. I think this is pretty much, this is pretty much all I have. This is 45 minutes. I'm happy to take questions. I think we have about 10-15 minutes. Chris?
Yeah, so I really like to talk. I had a question about the first part that I'll
Sure.
So when you ran your clustering algorithm, you didn't talk about, so you have to have some kind of a user trace to force it to go through the different functionalities and then get your timestamps in that cluster. So did you just sort of get a couple of friends to click and try the major functions, or is there some way to do that?
Well, there is in fact a reasonably principled way to do it, which is for large-scale applications, such as, say, Hotmail, you go to testers and ask them, well, what scenarios do you care about? Because they have performance goals there. They say, well, maybe loading the front page and then clicking the inbox and looking at the first message is something that we care about optimizing for. You take the same exact scenario, and that's what you're trained for. That's kind of the approach.
And if I understand correctly, what matters is not so much the order in which the clusters appear, but what gets clustered together. So the fact that you ask for directions and then ask for help later doesn't really matter. Right?
It shouldn't matter.
All the directions information comes as a bundle.
It shouldn't matter. It shouldn't matter. Yeah. Please.
So in this Ripley, it seems to me, and please correct me, that because ASP.NET is a fundamentally event-driven, stateful framework, that enables this to be possible. If you're not, I mean, because if you're saying on-click handlers on the server, you have to define that. You say on this, I just don't understand how you do it otherwise, right? Like if I'm a server is responding to a request, right? So I get a request coming in and says, here are some parameters, give me back some data, and the client handles that. That's how we usually develop Ajax applications. But how do you, I mean, who's writing that code and in what way is really doing it? Where does that happen?
Okay, so maybe there's some confusion here. So there's no ASP.NET dependency here at all, right? So the experiments we did basically were based on Volta, which is an independent technology that takes a bytecode application, essentially, I mean bytecode application, and kind of deploys it by partitioning it. Okay. So it has a client part and a server part. It has client state and server state. So the idea is that client state for the replica and the JavaScript would be basically one and the same, and then the server state would be shared.
So the developer is writing in whatever...
The developer is writing these things in C# or F# or some other thing like that, and basically then the compiler takes care of the rest.
And you're giving them an API, an event API that they are...
The event API is provided by Volta, so you have things similar to what you would find in JavaScript, which is like, you know, add event listener, blah, 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 that sort of thing.
Okay, so that's what enables this.
And that's what makes this particularly easy, let's put it that way. It's not impossible in other scenarios, but for instance, one thing we have to worry about in this system, which is basically a deterministic replay system, is what to do about non-determinism. If you have a, coin toss, what do you do? How do you make sure that the results agree within the replica and the client? And that sort of thing, virtualizing those functions, is made particularly easy by the fact that we have Volta on our side, and thereby we get sort of more control over the environment. Other questions? Yeah.
What about the data footprint, session data footprint on the server side because of the Ripley?
I'm sorry, what footprint?
Does it increase data, session data footprint on server?
How do you mean data footprint?
The session state it needs extra information about the session.
Right. Right. So there is. Right. So there is again. Basically there is more state, more memory that is being consumed. We basically did these experiments on small benchmarks to figure out what's going on there. Then we said, well, small benchmarks are great, but what happens in the real kind of large-scale application? And we went and measured the amount of client state you would have in a large application like Hotmail. It turns out that it's actually fairly manageable. It's a little bit bigger, but it's under 2 megabytes per replica in our experiments. So per connected client, correct. So we did it by actually taking Firefox and instrumenting its memory subsystem, garbage collection, and all these things to figure out what is the amount of JavaScript heap state as well as the dump state that you have to have available, and then translated those numbers over. Yeah.
So are you worried at all with Ripley about like high latency connections, mobile stuff like that? Is there any sort of condition where you could potentially run into trouble?
Well, no, it shouldn't really change things all that much. If you have a high latency connection, you would be, it's actually great to be able to migrate much of the execution over to the client, right? So you would basically run almost the entire application on the client, only communicating back to the server when absolutely necessary, right? With Ripley, we can actually do that without worrying about the security, right? So what would mostly execute on the client and then capture the events, and on the next RPC send them over, then the replica will do its job and then compare the results.
How do you know how long to keep the server component running? Do you just link it to a session, or?
We could link it to the session, yeah. We haven't looked at that kind of way too much, but I suppose we could serialize it in a way that's similar to the way you have sort of stateful server-side components serialized. In the back. Yes, you. Yes.
I have a question basically. Why do you think you can trust basically the sequence of events? So it's pretty much change in the state is quite long, right? I mean, it can't reuse anything. How can you ensure that it's actually more secure than just some logic? It's pretty much some manipulation of your
Right.
Sometimes you can know before the new one.
You cannot trust the sequence of events at all. We are not, but remember, the same situation, absolutely the same situation is true of a standalone application like a CGI script. It still gets some input, basically the same keystrokes and whatever events coming from the browser, and it has to operate based on that. So actually in the paper we have this argument that we formalized that says that effectively every attack that is possible against this model using sort of by tampering with the event stream was possible in the original non-distributed application. So if you have something like, I don't know, SQL injection application, Ripley is not going to help you out with that at all. You have to go use your static analysis or whatever use to detect SQL injection type things. But you have to take care of that sort of first, and then Ripley would come in. Oh, yeah.
If this is patent technology, or anyone can go ahead and use similar for open world scenario. JavaScript in the server side and
let's take that offline. I probably shouldn't be. Please, in the back. I'm sure people are watching. Yes, you.
So in Ripley, so we have the server side that has mimic the hand behavior, right? So is there any next way we still want to keep the JavaScript running at the client side? Client side, basically, from my point of view, probably can get rid of the computation at client side. Because client side, you can just send the input back, the output back to the client. Right?
It is true in a way. The client side is still kind of necessary there to show the picture. Right? If you have your Gmail, you still want your messages to appear. You still want these things to kind of happen. The alternative would be to basically, on the server, to keep an image of what the proper dump state should be, which would be returned on every response. And that way, it's kind of like sending bitmaps over.
But your replica can always send the output back, right?
Well, the output and what shows is not one and the same. The output might be you go and figure out somebody's, I don't know, age by the first name and last name. The output may be 17. Right? It doesn't mean that that's the only thing that the client side shows, right? It probably shows, you know, a whole bunch of other things as well, where you have, you know, in the corner somewhere you have 17. So the client side logic is still necessary for both accepting the input as well as producing the output. Your UI, so to speak, still needs to be there. But we can go and kind of remove the rest of the logic from the client side if we so desire. It's possible. Other questions? Yes.
So Ben, so it's really nice that you're being able to show that you can emulate, you know, the client side in your replica with a much smaller footprint.
Mm-hmm.
Nonetheless, you still pay for the cost of running the replica.
Of course.
And so, have you done some estimates in terms of if you were to do this for Hotmail?
Yes, we have.
How much extra cost would it be for you to run Ripley, you know, and buy the security while keeping latency really low for the
Right. So that's a great question. So in the paper, actually, we talk about this at length. We took Hotmail and basically sort of, I mean, Hotmail obviously is not written using Volta. It's hand-coded JavaScript for the most part. So there's no obvious way for us to take that and replicate it automatically, unfortunately. So we have to do these practice experiments to figure this stuff out. And basically, we went into the browser and measured the amount of browser state, as well as the various kind of, you know, issues with overhead. So the network overhead for Hotmail is the easiest thing to deal with. It's actually very small. You take a typical session, 10 minutes of you know, emailing, basically. The network overhead with Ripley for the events is under 1%. Nice. The memory overhead, we look at the heap within the browser and basically try to capture that and translate it over into what the emulator would produce. And it's basically 1.75 megabytes per running replica. And the target that we are trying to hit is about 100 users per machine, so it's actually fairly good too. Okay. Now the only thing that we haven't really had a good way to measure is basically throughput changes, because basically there is this additional component, code, execution, CPU utilization, so to speak, that we would like to also be able to measure, and that kind of scale-up experiment, unfortunately, we have not yet done. But we looked at the various ways in which JavaScript can be slow. So we went at looking at Hotmail to figure out what some of the long-running handlers are. Turns out those genuinely manipulate the DOM. And because there is, and do sort of various parsing and marshalling. And because that part is done in a way that's very efficient or non-existent just because we have no UI on the server, basically that part can be thrown away completely. We basically have empty methods implementing those things. So that gives us some encouragement and hope that we can actually scale this up considerably. Okay, if there are no other questions, thank you very much for coming.